R is a finite. So formal sum summation ai into xi I is equals to 0 to m. So that is equals to a naught plus a1 into x plus up to an into x power m, or a sequence of a naught comma a1 comma up to an. So where each and every coefficient is belongs to real number. So ai is belongs to r. So that is ai are called coefficients of f of x. So in polynomial, each and every coefficient is belongs to real number. So this is called polynomial. So the degree of f of x is the largest integer I, for which the ith coefficient of f of x. So for example, x cube plus 2x square plus 1 is equals to 0. So this is one polynomial of degree 3. So here a cube a3 into x power 3 plus a2 into x square plus so this is a0 a1 a2. So these are the coefficients. So x3 x power 3 coefficient is 1, so x square coefficient is 2, so this is constant term. So degree of the polynomial is 3, so highest to power in given polynomial, so x cube. So here the degree of f of x is the largest integer I, for which ith coefficient of f of x. So that is is not 0. So here if an is not is equal 0, then the degree of f of x is n, and it is written as degree of f of x is equals to n. And so this is the polynomial degree definition. So this is polynomial. So here degree of the polynomial is n. Here highest coefficient. So here highest coefficient is x power n. So x power n coefficient is a naught. Okay? So a naught is not an is not is equal 0. So then degree of the polynomial is n. So here, so next constant polynomial. A polynomial is said to be a constant polynomial if its degree is 0. Okay? So next constant polynomial definition. A polynomial is called a constant polynomial if its degree is 0. So the coefficient an is called leading coefficient of f of x if it is an is equals to 1. So then f of x is called monic polynomial. So constant polynomial is nothing but, so like f of x is equals to some constant terms 2 or 3 4, like constant terms is nothing but x power 0. So here x power 0. So these are the constant polynomials. F of x is equals to 2 into x power 0 is nothing but 1. So f of x is equals to 2. So these are called constant polynomials. Okay. Next, equality of polynomials. The polynomials f of x equals to a naught plus a1 into x plus up to an into x power n, and g of x is equals to b naught plus b1x plus up to bn into x power n are said to be equal if for every integer greater than or is equals to 0, ai is equals to bi. Thus, the two polynomials are equal if their corresponding coefficients are equal. So here f and g, these two equal polynomials is said to be equal polynomials. So each and every coefficient a naught is equals to b naught, a1 is equals to b1, an is equals to bn. Each and every coefficients are equal. Corresponding coefficients, x coefficient is equals to here a1, here b1. So a1 is equals to b1. So next x square coefficients, a2 is equals to b2. So next x cube coefficients, a3 is equals to b3. So like xn is equals to an is equals to bn. So if the two polynomials are said to be equal, each and every coefficient of the polynomials are must to be equal. Okay. So this is equality of polynomials. So next multiplication. If f of x is equals to a naught plus a1x plus up to am into x power n, and g of x is equals to b naught plus b1x plus up to bn into x power n, then the addition of f and g is denoted by f of x plus g of x. So f of x plus g of x is equals to c naught plus c1 into x plus up to Ci into Xi, for which I Ci is equals to Ai plus Bi, and Ai is equals to Bi plus Ci. So this is A naught plus B naught is equals to some C naught. So next, X coefficient A1 plus B1. So A1 plus B1 is equals to some real number constant. So here A1 is equals to A1 plus B1. So A1 plus B1 is equals to some real number constant. So here C naught real number. Sum of two real numbers is equals to so real number. So here B1 plus A1 is equals to C1, like this, using this condition. Ci is equals to Ai plus Bi. So next x square coefficient is C2. So next up to xi coefficient is Ci. Okay. So this is sum of two polynomials plus up to ck into x power k. So where c t is equals to at into b naught plus at minus 1 into b1 plus at minus 3 into b2 plus up to a naught into bt. So we can multiply each and every element a naught to the total polynomial a naught into b naught plus a naught into b1 plus a naught into b2 plus a naught into bn into x power n. So next term a1. So we can multiply a1 with total g of x. So a1 into b naught plus a1 into b1 plus a1 into b2. It's like this. a1 into bn. Okay. So we can multiply each and every term in f of x to g of x. So we are getting f of x into g of x. The product of two polynomials sign. The sum of two polynomials is f of x plus g of x sign. The product of two polynomials f of x into g of x. So these are the sum and product of the two polynomials. Next, if R is integral domain and f of x and g of x are two non-zero elements of R of x. So degree of f of x into g of x. The degree of f of x into g of x equals to the degree of f of x plus degree of g of x. You know? So degree of f of x into g of x is equals to so degree of f of x plus degree of g of x. So this is only note condition. So we can remember this condition. Degree of f of x plus g of x is equals to degree of f of x plus degree of g of x. So next to primitive polynomial, content of polynomial, monic polynomials. So here, this is very important theorem, Einstein criterion for long question. So before going to this theorem, so we have to learn primitive polynomial, and monic polynomial, irreducible polynomial, and also the product of two primitive polynomials is again a primitive polynomial. So this theorem also, the product of two primitive polynomials is again a primitive polynomial. F of x and g of x are two primitive polynomials, and the product f of x into g of x also a primitive polynomial. You know? So definition, primitive polynomial definition. Let R be a unique factorization domain UFD. Then a polynomial f of x belongs to R of x is called primitive polynomial if GCD of its all coefficients is equals to 1 or unity. So GCD of all coefficients is equals to 1. Primitive polynomial definition. So for example here, So f of x is equals to 2 plus 3x minus 4x square belongs to z of x. So your GCD of all coefficients. So your coefficients are constant 2, x coefficient 3 and x square coefficient is minus 4. So GCD of 2 comma 3 comma minus 4. All the coefficients in the polynomial. All the coefficients in the polynomial is 1. So GCD is nothing but greatest common divisor. So GCD is greatest common divisor. So GCD is 1. So which is unity in Z. So therefore f of x is primitive polynomial. Okay, na? So this is primitive polynomial definition. So again definition, let R be a unique factorization domain, then the polynomial f of x belongs to R of x is called primitive polynomial, then GCD of all its coefficients is unity or 1. So then we can say that, so given polynomial is primitive polynomial. So example 2 plus 3x minus 4x square. So here all coefficients GCD is 1. So then we can say that f is primitive polynomial. So next here another example 2 plus 4x plus 10x square belongs to z of x. So here GCD of 2 comma 4 comma 10. So greatest common divisor is 2. So 2 divides all the elements. So 2 divides 2, 2 divides 4, 2 divides 5. So 2 divides 10. So GCD of 2 comma 4 comma 10. All the coefficients GCD is 2. So which is not a unit. So this is not a unit element. So unit element is nothing but 1. So here not a unity. So therefore f of x is not a primitive polynomial. Is clear? Any doubt? Primitive polynomial. So primitive polynomial is nothing but GCD of all coefficients in the polynomial is equals to 1. Then we can say that the polynomial is primitive polynomial. So otherwise the polynomial is not a primitive polynomial. So next, content of a polynomial. So let f of x be a non-zero polynomial in C of x. So this is nothing but complex numbers such that f of x is equals to a, f of x where a belongs to R and f of x is primitive, a is called content of the polynomial, and f of x, it is denoted by C of f of x or CF. You know, C of f of x or C into f. So for example, f of x is equals to 5 plus 10 into x. So 5 plus 10 into x belongs to z of x. So in this polynomial 5 is common. So 5 common. So 5 is common. 5 of 1 plus 2x. So where f1 of x is equals to the new polynomial. So this is assumption is nothing but f1 of x. So f1 of x is equals to 1 plus 2x. And this polynomial must be primitive polynomial. The GCD of all coefficients 1 comma 2. The GCD of 1 comma 2 is equals to 1. So therefore f1 of x is primitive polynomial. Therefore the content of the polynomial C of f of x is equals to 5. You know, so this is content of the polynomial. And here also, so next second example, f of x is equals to 2 plus 4x plus 10 into x square belongs to z of x. So here in this total polynomial 2 is common. So 2 is common and remaining polynomial 1 plus 2x plus 5x square. So in this total polynomial coefficients GCD of 1 comma 2 comma 5. So 1 comma 2 comma 5 is 1. So therefore this polynomial is primitive. Okay, primitive polynomial. So therefore content of the polynomial C of f of x is nothing but 2. A. So this is A. A is common. So A into f1 of x. So but f1 of x is primitive polynomial. You know, so this is primitive polynomial definition. So definition once again. Let f of x be a non-zero polynomial in R of x such that f of x is equals to a into f of x. So this is a into f of x. The multiplication here. Here multiplication. F of x is equals to a into f of x. So where f1 of x is primitive, then a is called content of the f of x, and it is denoted by c of f of x or c into f of x. So example, we are taking common. So 5 is common, 1 plus 2x. So 1 plus 2x is a polynomial and it is primitive polynomial because the GCD of all coefficients in the polynomial is equals to 1. So therefore, content of the polynomial is 5. Okay. So these are the definitions. So primitive polynomial. So primitive polynomial is nothing but all the coefficients in the uh, GCD of all coefficients in the given polynomial is equals to 1. So then we can say that the polynomial is primitive polynomial. So next, the content of the polynomial is nothing but, so we can take common in given polynomial and remaining polynomial should be primitive. Then we can say that the polynomial is content is A. So next, monic polynomial. So a polynomial f of x is equals to a naught plus a1 into x plus up to an into x power n belongs to R of x is said to be a monic polynomial if leading coefficient is equals to 1. So that is an is equals to 1. So highest degree, so degree leading coefficient an is equals to 1. So then we can say that the polynomial is monic polynomial. So for example, f of x is equals to 7x plus 3x square plus x cube. So here degree of the polynomial is 3. So leading coefficient of x cube is 1. So that is a3 is equals to 1. So leading coefficient of highest degree is 1. So therefore f of x is monic polynomial. Is clear? So g of x also monic polynomial 9 minus 3x plus 4x cube plus x power 6. So this is also monic polynomial. So because degree of the polynomial is 6. So degree is 6 and leading coefficient of x power 6 is 1. So therefore f of x and g of x, these two polynomials are monic polynomials, and GCD of all coefficients. So GCD of 9, 3, 4, 1. So GCD of 9 comma minus 3, okay, minus 3 comma 4 comma 1. So is always 1. So is nothing but every monic polynomial is content is 1. Is nothing but every monic polynomial is primitive polynomial. So every monic polynomial is primitive polynomial. So GCD of all coefficients in monic polynomial must be equals to 1, always equals to 1. So therefore every monic polynomial is always primitive polynomial. Okay. Like this. So next note point. So every monic polynomial in Z of x is always primitive polynomial because GCD of monic polynomial is equals to always 1. So therefore is always primitive polynomial. Okay. So next theorem. So theorem, if f of x comma g of x belongs to z of x are primitive polynomial, then the product f of x into g of x is also primitive. So this is the question. So this one, 12.5.2. So if f of x and g of x are primitive polynomials, then the product f of x into g of x is also a primitive polynomial. So 12.5.2 theorem. The product of two primitive polynomials is again a primitive polynomial. So this is f comma g are primitive polynomials. Then the product f and g also a primitive polynomial. So proof f of x is equals to a naught plus a1 into x plus up to ai into x power I plus am into x power m, and am is not is equals to 0. G of x is equals to b naught plus b1 into x plus up to bj into x power j plus dn into x power n. So these are the two primitive polynomials. So we are taking, so f comma g are two primitive polynomials. A naught am is equals am not is equals 0 and bn not is equals 0. Is nothing but these are two leading coefficients are not is equals to 0. So big two primitive polynomials. So now the product f and g. So product of two polynomials c naught plus c1 into x plus Cj plus Ci plus j is equal x power I plus j up to so on Ck into x power k in bracket Ck is not is equals to 0. So next we are taking two primitive polynomials and product of two primitive polynomials f of x into g of x is equals to c naught plus c1 into x plus up to cj ci plus j into x power I plus j plus up to so on ck into x power k, where leading coefficient ck is not is equals to 0. So where these coefficients c naught equals to c1, c1 is equals to c2 is equals to up to ci plus j comma ck values. So where c naught is equals to coefficient c naught plus a naught plus b naught. So c1 is equals to a naught plus b1, a naught into b1 plus a1 into b naught. So this is c1 coefficient. So next ck coefficient a naught into bk plus a1 into bk minus 1. Next coefficient a2 into bk minus 2. So next up to plus ak into b naught. So these are the c naught, c1 up to ck coefficients. If positive, suppose f of x into g of x is not primitive. Suppose f of x into g of x is not primitive polynomial. So that is nothing but, so primitive polynomial is nothing but GCD of all coefficients is equals to 1. So not primitive is nothing but, so GCD of c naught comma c1 comma up to ck is not is equal to 0. So not is equals to 1. So then there exists a prime number p. So prime number p such that p divides c1 ci for I is equals to 1 to k. So this is equation number 1. So p divides ci for I is equals to 1 to k, equation number 1. Since f of x is primitive polynomial, so p does not divides a naught and p does not divides a1. For some I is equals to 1 to m, so p divides a naught comma, p divides a1 comma, p divides a2 up to p divides ai minus 1. P does not divides a naught. So this is equation 1. So similarly g of x also p does not divides bj. So for some j is equal to 0, 1, 2 up to n. So j is the index such that, so consider the coefficient ci plus j in f of x into g of x. So ci plus j coefficient, so a naught plus pi plus j plus a1 plus a1 into bi plus j minus 1 bi ai plus up to ai minus j into b naught. From equation number 1 and 2, p does not divides ai and bj, because here, so this coefficient p does not divides ai. So p does not divides ai and p does not divides bj. So therefore, from equation number 1 and equation number 2, so p does not divides ai and bj. So p does not divides ai and bj, and also p does not divide ci plus j, ci plus j. So which is contradiction to equation number 1. So which is contradiction to equation number 1, because p divides ci. So for I is equals to 1 to k. So this is contradiction to equation number 1. Our supposition that f of x is g of x not a primitive polynomial is wrong. Hence, f of x in g of x is primitive polynomial. You know? So this is theorem. Theorem statement: the product of two primitive polynomials is again a primitive polynomial. So this is theorem. So this is 12.5.2 theorem. The next definition, the content of polynomial. So we know already content of the polynomial definition. The greatest common divisor of integer equals to 1. So then we can say that content of the polynomial. The next definition, let R be a integral domain. A non-constant polynomial f of x belongs to R of x is said to be irreducible over R. So irreducible polynomial if whenever f of x is equal to g of x into h of x. So this is irreducible polynomial definition. So f of x is equals to g of x into h of x. So with g of x comma h of x is belongs to R of x, then one of these two polynomials degree should be 0. So that is one of the g of x or h of x is constant polynomial. If f of x is not irreducible, then we can say that it is reducible polynomial. So irreducible polynomial definition. So irreducible polynomial is nothing but f of x is equals to some product of two polynomials. So g of x into h of x. So if f of x is said to be irreducible polynomial, irreducible polynomial is nothing but f of x can be written as product of two polynomials. F of x is equal to g of x into h of x. So in this product, at least one of the polynomial is so f of x is equals to g of x and h of x. In these two product of two polynomials, at least one of the polynomial degree should be 0. Is nothing but so degree of the polynomial is 0 is nothing but constant polynomial. So in these two polynomials, product of two polynomials, so g of x and h of x. In these two polynomials, at least one of the polynomial degree should be 0 is nothing but either g of x is constant polynomial or h of x is constant polynomial. So then we can say that f of x is irreducible polynomial. So if f of x is not reducible, then we can say that irreducible, then we can say that it is reducible polynomial. It's clear? So reducible and irreducible definition. This is definition. So irreducible polynomial, a non-constant polynomial f of x is said to be irreducible. So whenever f of x is equals to g of x into h of x, so with g of x comma h of x belongs to f of x. So with one of the g of x or h of x is 0th degree polynomial is nothing but so in these two polynomials, at least one of the polynomial is constant polynomial. So for examples, so f of x is equals to x square plus 1. So f of x is equals to x square plus 1 is not irreducible polynomial. So irreducible polynomial is nothing but so f of x can be written as g of x into h of x. In these two polynomials, at least one of the polynomial is constant polynomial is nothing but so 0th degree polynomial. So here f of x is equals to x square plus 1 is not irreducible over c. So over c, so f of x can be written as a square minus b square formula, a plus b into a minus b, x plus I into x minus I. So these are the complex numbers, a plus I complex number and x minus I. So these are the complex numbers. So that's why we are taking over c of x. Okay, over c of x. So this is in these two polynomials, f of x is equals to g of x into h of x. So at least one of the polynomial should be 0th degree polynomial or constant polynomial in our definition. So but here, so first f of x equals to x plus 1 into x minus 1. So in these two polynomials of degree 1, 1. So therefore, so these are not a 0th degree polynomial. So therefore, f of x is irreducible over c of x. So not a irreducible is nothing but f of x is reducible polynomial. So this is So f of x is reducible polynomial over C. So therefore f of x is reducible polynomial over C. Hence f of x is reducible over C. So next example, f of x is equals to x square plus 1. So is irreducible over R. So f of x is equals to x plus I into x minus I. So these are does not belongs to R. Is clear? So these are the x. So roots of f of x is belongs to complex numbers plus I minus I. So x plus I into x minus I. So does not belongs to R. So is given over the field of real numbers, is given real numbers. So but we are getting roots are complex numbers. So x plus I into x minus I. So does not belongs to R. So these are does not belongs to R. So therefore f of x is equals to x square plus 1 is irreducible over Q. So similarly over R. So next f of x is equal to x square minus 2 is irreducible over Q. So x plus 2 x plus root 2 into x minus root 2. So third example, we can write x plus root 2 into x minus root 2. So these are the irreducible over Q. Root 2 comma minus root 2 belongs to Q. So therefore, so this is irreducible polynomial over Q. So this is irreducible polynomials. So this is example for reducible polynomial. So first one is example for reducible polynomial. So this is 12.5.6. So definitions for reducible polynomials and irreducible polynomial line with examples. Okay. So these are the examples. So here also there are examples. X square plus 1, x plus I into x minus I. X minus I is reducible over Z2. So these are the examples. So next, this is very, very important theorem. Einstein criterion. F of x is equals to a naught plus a1 into x plus up to an into x power n be a polynomial with integer coefficients. Suppose for some prime number, so p naught comma p, so p does not divide an comma p divides a1 comma p divides a2 up to p square does not divide a naught. Then f of x is irreducible and irreducible over rational numbers. Okay, so this is theorem. So Einstein criterion, let f of x is equals to a naught plus a1 into x plus up to an into x power n belongs to z of x with n greater than or is equals to 1 if there exists a prime number. So there is a prime number p such that p square does not divide a naught comma p divides a naught, p divides a1 up to p divides an minus 1 comma p does not divide an. So then f of x is irreducible over rational number or q, is irreducible over q. So these are the important theorem. P divides a naught comma p divides a1 comma p divides a2 comma up to p divides an minus 1. So these are a naught, a1, an minus 1 are the coefficients of the given polynomial. So these are the coefficients of the given polynomial, and so p does not divide leading coefficient an, and p square also does not divide a naught. You know? So p does not divide an, p square does not divide a naught. So p is nothing but any prime number. So p is any prime number. So prove to show that f of x is irreducible over q. Irreducible polynomial is nothing but, so previous definition, irreducible f of x is equals to g of x into h of x. F of x is equals to g of x into h of x. So If f of x is said to be irreducible polynomial, so this can be expressed as product of two polynomials. F of x should be expressed as product of two polynomials. So g of x into h of x in these two polynomials. So one of the polynomial should be constant polynomial or zeroth degree polynomial is nothing but, so g of x or h of x should be constant polynomial. You know, to show that f of x is irreducible over q. It is enough to show that f of x is reducible over z. Okay. So it is enough to show that f of x is irreducible over z. So z is nothing but always it is irreducible over q also. So if possible, so suppose f of x is, if possible, suppose f of x is reducible over z. So but our assumption, so we have to show that irreducible polynomial. So but our assumption nothing but, so f of x is reducible over z, then f of x is equals to g of x into h of x. By using definition of reducible polynomial, f of x is equals to g of x into h of x. So where, so g of x comma h of x is belongs to z. So this one over z. So we are taking h of x comma g of x is belongs to z. So next, degree of g of x is greater than or is equals to 1 and degree of h of x is greater than or is equals to 1. So because reducible polynomial is nothing but degree of polynomials. So f is equals to g into h. So reducible polynomial definition, a polynomial f is said to be a reducible polynomial. So f can be expressed as product of two polynomials g and h. In these two polynomials, degree at least 1. So degree of the polynomial is at least 1. So degree of g of x is at least 1 and degree of h of x is at least 1. In case less than 1 is nothing but 0th degree polynomial. So 0th degree polynomial is nothing but it is irreducible polynomial. So therefore degree of g of x and h of x is greater than or is equals to 1. So this is reducible polynomial definition. So we are taking degree of g of x is greater than or is equals to 1 and degree of h of x is greater than or is equals to 1. So let g of x is equals to c naught plus c1 into x plus up to cr into x power r, where 1 less than or is equals to r less than or is equals to n. So this is nothing but, this indicates 1 less than or is equals to r less than or is equals to n is nothing but the degree of the g of x is at least 1. The degree of g of x is at least 1. Here also, degree of h of x is also at least 1. So here h of x is equals to b naught plus b1x plus up to bn into x power s. So bs into x power s, where 1 less than or is equals to s less than or is equals to n. So these are the degrees greater than or is equals to 1. So we are consider g of x as c naught plus c1x plus up to cr into x power r. H of x is equals to b naught plus b1x plus up to ps into x power s. So since f of x is equals to g of x into h of x, using this condition, reducibility condition, reducible polynomial condition, so f of x is equals to g of x into h of x. So f of x is equals to a naught plus a1x. So is given in question f of x value, f of x polynomial, f of x is equals to a naught plus a1x plus up to am into x power n. So that is equals to, so multiply these two terms. So we are getting c naught b naught plus, so c naught into b1 in plus c1 into b naught x plus cr into br x power r plus s. After multiplication, we can write product g and h value. So next we can compare. So we can compare coefficients. A naught is equals to, a naught is equals to b naught plus c naught, c naught plus b naught. So this is 0. So c naught plus b naught. A1 is equals to c naught b1 plus a1 b naught, c1 b naught. So next an is equals to cr into br. After multiplication of these two polynomials, so we can compare both sides. So we are getting A naught is equals to C naught plus B naught, and A1 is equals to, so C naught B1 plus B1 C1. So next, AN is equals to BR into CR. So given that, so using condition given P divides A naught is given condition. So this condition, this one, P divides A naught, comma, P divides A1, comma, P divides A2 up to P divides AN minus, comma, P does not divides AN, and P square does not divides A naught. So using this condition, first one, P divides A naught. So P divides A naught and P square does not divides A naught. So P divides A naught is nothing but, in place of A naught, we are substitute C naught into B naught. So P square does not divide C naught into B naught. So here, so this can written as P divides C naught and P does not divide B naught, or P does not divide C naught and P divides B naught. So here two cases. So we are taking two cases. So P divides C naught, or P does not divide B naught, or P divides C naught, or P does not divide B naught. You know, these two cases. So suppose, so first case, suppose P does not divide C naught and P divides B naught, and also given that P does not divide AN. For this condition, in this, so P does not divide AN. So using this condition, the first case, P does not divide C naught and P divides P naught. Given P does not divide AN, so P does not divide. So AN is nothing but BR into CR into BS. So this coefficient AN is nothing but BR into CS. So this is from equation number 2. So next, P does not divide CR and P does not divide BS. So this one. So P does not divide CR and P does not divide BS. So since P divides B naught and P does not divide BS. So here we are taking P divides B naught. So P divides B naught and we are taking P does not divide BS. These two conditions. So these two conditions. So P divides B naught and P does not divide BS. So let M be the first coefficient in f of x. So which is not divisible by P. So let M be the first coefficient in f of x, so which is not divisible by P. So that is P divides B naught, comma, P divides B1, comma, up to P divides Bm minus 1. So P does not divide Bm where m is less than or is equals to s. So we are taking a polynomial, so which is less than or is equals to s. So all coefficients are m is less than or is equals to s. So this is equation number C. Equation number 3. So next consider am is equals to c naught bm plus, so c1 into bm minus 1 plus up to cm into b naught. So since p divides bm minus 1, p divides bm minus 2, p divides b1, p divides b naught from equation number 2. So before m, we can divide all the coefficients by p. So p divides bm minus 1. So p divides bm minus 2. P divides b1. So p divides b naught from equation number 3. So p divides c1 into bm minus 1. P divides c2 into bm minus 2. So multiply. So this one, I first g of x is divisible by p. So p divides c naught, p divides c1. So like this. So we are getting p divides c1 into bm minus 1, p divides c2 into bm minus 2, p divides cm minus 1 into b1, p divides cm into b naught. So next, p divides sum of all the elements, c1 into bm minus 1 plus c2 into bm minus 2 plus up to cm minus 1 into b1 plus cm into b naught. This is equation number 4. So we have So we have P does not divide C naught and P does not divide BM from equation number 3. So therefore P does not divide C naught into BM. So equation number 5. From equation number 4 and 5, we are getting P does not divide BAM. So this is contradiction to our assumption. So therefore, given that P divides A naught, P divides A1, P divides AN minus 1, P does not divides AN. So we are getting M is equals to N. So which is contradiction to our assumption. So therefore, f of x is irreducible, reducible over z is wrong. So hence f of x is reducible over z. So this is the theorem, Einstein criterion. So this is very important theorem. So for example, x square minus 2 is irreducible over q. So x square minus 2 is irreducible over q. Right, f of x is equals to x square minus 2 belongs to z of x. So minus 2 is constant plus 0 into x, 0 into x plus 1 into x square. So this is the polynomial. So next to, so compare this polynomial with a naught plus a1 into x plus a2 into x square. So where coefficients are a naught is equals to minus 2, a naught 0, a naught is minus 2, a1 is 0, a2 is equals to 1. So by using Einstein criterion, p divides a naught, p divides a1, p does not divide last term an. So p does not divide an is nothing but p does not divide a2. So next square does not divide a naught. So we are choosing p is equals to 2, or we can take any prime number. P is prime, so we can take any prime number. So we have p divides a naught, 2 divides minus 2. So p divides a1, so 2 divides 0. So next, p does not divide a2. So 2 does not divide 1. And p square, so 4. Here square is there, 2 square. So 2 square 4 does not divide minus 2. So therefore, f of x is irreducible over q. So this is example of Einstein criterion. So this is example for Einstein criterion. Next note, a polynomial f of x is irreducible if and only if f of x plus 1 also irreducible. Is clear? So this is the f of x is irreducible, then f of x plus 1 also irreducible polynomial. This is Einstein criterion 12.6.1 theorem with example. Next, Gauss lemma. If R is a unique factorization domain and if f and g are in R of x, then C of f into g is equals to C of f into C of g. So C is nothing but content of the polynomial. So in particular, the product of two primitive polynomials is primitive. So this theorem is already completed. The product of two primitive polynomials is again a primitive polynomial, and we can take content on both sides. It will also do C of f into g is equals to C of f into C of g. So this is Gauss lemma. So next, very important theorem, fundamental theorem of Galois theory. So this is 100% question in your examination. So this is the theorem. So fundamental theorem of Galois theory. So we can write statement also. So this is the statement, and this is the proof. So we will discuss on next class fundamental theorem of Galois theory. So this is the statement. Let E be a Galois extension of F. Write S is equals to K divides K is subfield of E containing F, and T is equals to H divides H is subgroup of G of E over F. So we can prove that these three conditions. Okay.
Thank you, sir.
Okay. We'll discuss next class fundamental theorem of Galois theory. So very important theorem. So don't miss.
Yes, sir.